Oh, right. Thank you. My talk actually will have two pretty much disjoint sections. So the first part is about some two-loop computations to a complete set of observables, mainly electroweak position quantities that are relevant for the Z-pole measurements at lab and maybe some future A plus A minus collider. And this is work I'm doing together with these people over here. And the second part of the talk will be not about any concrete application, but just as a building block for some, namely having to do with certain three-loop integrals for a general set of masses. Okay, so to start off with the first topic, the electroweak precision corrections. So I don't want to give much of an introduction into that topic, but I guess many of you know that these are important for testing the standard model and also testing potential new physics contributions. And because of the level of experimental precision that we have, we also need to compute higher order corrections in the standard model to match that. And so in particular, these would be vertex corrections of this sort, where this is a Z boson. These are various standard model fermions here in the external lines. And then in the loops, you know, everything you have in a standard model can appear. And so the current state of the art for doing that is two-loop corrections, like some of these sample diagrams that are shown over here, which were computed over many years by contributions of many people. So this is probably not a complete list of references that I'm giving here, and I apologize for any that are omitted. In addition, we also have actually partial corrections that go beyond two-loop at a 3 and even 4-loop level, and these are corrections that are enhanced by powers of the top Yukawa coupling. So they are more important, and they are also technically easier to compute. That's why they are available. But actually, even at the two-loop level, the results that are available so far are not really complete. For the most part, what has been computed for several quantities are just diagrams that contain closed fermion loops, like the ones shown here. So you see those closed fermion loops inside these diagrams. These are numerically more important, and it's also a smaller set of different integrals you need to consider. Therefore, they have been done first. But our goal is basically trying to compute the remaining two-loop diagrams, which we call the bosonic ones. That means without closed fermion loops. And so there are several pieces that are necessary for accomplishing this task. So first of all, we have to compute those vertex corrections. We also have to compute the appropriate renormalization, for which we use on-shell renormalization. The renormalization constants involve self-energies. That's pretty well known how to do arbitrary two-loop self-energies. And in addition, for the vertex diagrams, there are simpler and more complicated ones. The simpler ones are types that are of this sort, you know, where you have a subloop bubble that can also appear if this bubble is not a fermion, but say a W boson, as an example. These are relatively straightforward to do by using a dispersion relation for the subloop bubble. And then in addition, there's a set of diagrams with a set of integrals which are less trivial than these. So these are basically three-loop integrals that don't have any simple subloop topology. So here are a few examples of those. You know, these can be planar type and non-planar type, and you know, somewhere some propagator got cancelled. And they can have, you know, various masses in the propagators, which are not identical. So the approach we pursue for computing these is one that uses relatively heavy contribution of numerical integration. And currently for numerical integrations, there are two main methods which are fairly generally applicable for a large number of different applications, and for which there are also actually a variety of public tools available. One is sector decomposition, which we heard about in the previous talk by Stephen. And the other one, which I will talk about more here, is using Mellin-Barnes representations. And in our approach, we actually use these Mill-Advanced representations directly for the set of integrals that appear in our problem. So we are not trying to do a reduction to master integrals. So in total, actually, we have a set of about 700 different non-trivial integrals that are treated with this method. So to give a quick introduction into Mill-Advanced representations, so the idea with that is if you have a Feynman parameter integral, what you typically have is you have a multidimensional integral over Feynman parameters, and then you have, these, you have these polynomials, which are a sum of terms in the integrand. And with the Mill-Advanced representation, you can write this sum of terms actually as a product of terms and then various gamma functions over here. But there are actually some constraints on this. So the integral that is being performed is now an integral in the complex plane. And the contour of this complex integration has to be chosen such that all the poles of these gamma functions are either to the left or to the right of this contour. And sometimes this is only possible to satisfy if you shift the number of dimensions away from 4. Now, in the end, of course, we want something with the limit dimensions going to 4. And so if you, use this parameterization here and then just let the dimension go to 4, what happens is that some of the poles might actually cross the contour. And then you have to pick up the residue of that contribution. And that's actually not a problem, but a feature, because it turns out that these residues give you exactly the divergent pieces of your integral. So contributions that go with powers of 1 divided by epsilon. And then the remaining integrations that are left are done numerically. That's the idea. However, that's sometimes not as simple as it looks like, because if you use, physical kinematics in Minkowski space, you sometimes get contributions like this, so where you have minus momentum squared to some power. And well, if I take this minus something and I split it up into complex coefficients, complex pieces, I see that there's this minus sign produces an e to the, something with the imaginary part here in the exponent. And as I said, I'm integrating some contour in the complex plane, and this is by default parallel to the imaginary axis. So I get an additional I from that. That in the end produces something which is real in the exponent, and therefore either above or below, either side of it, it has a tendency to blow up, and therefore doesn't converge well numerically. So one has to somehow deal with that. One possibility is to say, well, instead of integrating parallel to the imaginary axis, I might, tilt my contour and integrate with some different slope. The advantage of that is I get an additional piece in the exponent, which is also real. And I can basically tune the angle of this deformation such that it cancels the piece that is not desirable. So for this particular integral, that's pretty straightforward and works very well. It's not always that easy, because I can have situations where actually I don't have any relevant ratio of parameters. For instance, this is a vertex integral which depends on one external momentum squared and one internal mass. But I may be interested in a kinematic region where those two are identical. Then this is just 1 in this ratio, and if I tilt the contour, I actually don't get anything interesting in the exponent from this 1. So therefore, this does not work always. So one has to also have some other arrows in the quiver. And one other thing one can do is to, instead of a tilt of the contour, do a shift of the contour. So we are basically moving this contour to the left or to the right. Of course, when we do that, we are crossing poles of the gamma functions again. So we need to pick those up, but that's a finite number of them. The advantage we get, on the other hand, is that actually if you shift it in the right direction, the behavior of the integrand for large values of the integration variable improves. So for this example up here, for instance, the original integral, if I go out, to large values of the integration variable goes like the integration variable to the power -2, and then there's an additional piece which you get from just studying your numerical result, and that's here -0.7. So overall, it just goes to the power -0.6. So it doesn't converge well at all. However, if I shift the contour by n integer values, I get an additional suppression -2n. Oh.
Very funny.
And so if I do that several times, I will have a good behavior of the integral. In addition, what also happens is actually because if I shift the contour, there are those residues I need to pick up explicitly. The remainder I need to do numerically is actually numerically smaller. So this can be seen here. This is the number of shifts I do. So 1, 2, 3, 4, 5, and so forth. These integer steps of 1, 2, 3, and so forth. Originally, this is basically the magnitude of the numerical integral that I had. And then after I pick up these individual pieces, the remaining numerical integral is just this much, many orders of magnitude smaller. So it's basically a compromise, right? Doing an infinite sum over all poles is actually oftentimes not working so well, but here we are doing just a finite sum, and then again the remainder is done as a numerical integral. Now for this simple example here, which is just a two-dimensional integral, this works beautiful, as you can imagine. However, for more complicated integrals, it's sometimes hard, to find what are the right contour shifts one needs to do. My collaborator, Johan Usovic, has basically come up with strategies how to choose these contours. It's not fully automated for any imaginable integral that you can think of, but at least for a large class of them, it works in a pretty much automated way. And I guess at some point there will be a public package called Numerics that does that. So here are some examples of certain integrals. And for comparison, I saw some results from SecDec. That's still an older version of SecDec, so the newer version might be more efficient. But just to give some idea of how the two compare. So this is an integral which has a number of massless lines, then some lines that have a mass of W mass and some of a top mass, and the external scale is the Z mass. You get this result with SecDec running for a fairly long time. And with the MB numerics method, the same result actually with higher precision can be obtained much faster. Then there are also examples which actually just came up before. If you're sitting right on the threshold, there's the difficulty with the contour deformation method, that you might not converge at all very well. So this is one example of this. So there's an internal mass, which is the Z mass, and the external momentum squared is also Z. SecDec unfortunately doesn't converge, but with the MB numerics method, this can be still done. And well, to have a comparison for this one, actually, there's an analytic result. That's fine. So to compare these techniques in the end, there's still pluses and minuses. So sector decomposition definitely has the advantage that it's fully automated. There are tools, that work at least conceptually for pretty much any integral. But there may be issues about the numerical stability and the amount of computing time it takes to get a good precision. The Mellon-Barnes method, on the other hand, is at this point not fully automatic. There's some partial automatization, which works pretty well for our project. Cannot promise that it would work for any other project. But it has the advantage you get, very good numerical precision within a reasonable amount of time, at least for two-loop integrals. So now coming to my second part, which is looking a little bit into the future where we might want to do general three-loop corrections for some processes involving not just massless, but general massive propagators. And one building block for that will be integrals which actually don't have any external momentum scales. In particular, you would encounter it, for instance, if you do something like a low momentum expansion or something like that. And so I was interested in tackling that problem, as an intermediate step for some phenomenological application. Now it turns out you can do a reduction to master integrals for problems of this kind, and it turns out there are actually only 3 master topologies that need to be considered, which are shown here. So this one has 4 different propagators. One of them is taken with power 2. This one has 5 different propagators, and this one has 6 different propagators. So basically, I want to compute these master integrals for arbitrary masses in the propagators. I also want to be able to do this with high precision and relatively efficiently, so I'm not trying to use a method which works general for any three-loop integral, but just try to apply this to this set of vacuum integrals. The approach I'm taking here is to use dispersion relations for internal subloops. So I'm starting off with this situation where I have a product of 2 one-loop bubbles. So these are B0 functions, actually one with the taken the derivative of it because of the double propagator. But you know these B0 functions very well, and they can be written as a dispersion relation. It looks like this, and so this is an integral over some cut parameter, and the integrand, is basically given by the imaginary part of these functions. This is very well known. Now, how do we make use for our three-loop integral? Well, the idea is basically I take this external momentum which flows through this product of bubbles, and I tie this end to that end and say this is a third loop momentum. Then I get this diagram over here. And the expression I get is basically, okay, here I have this third loop integral on top of the expression I had here. But this integral can be performed immediately, right? Because the third loop momentum only appears down here. So this is just a basic one loop A0 function. So I can write it like this, and then the remaining integral over this cut parameter S could be done numerically, but it's just a one-dimensional integral. Now there's one problem because this integral has UV divergences, and numerical integrals don't like UV divergences, so we somehow have to make it finite. Well, one way to do that is one can identify this combination of same topology, but with some masses set to 0. And it turns out that this sum has the same UV singularities as this general case. But because here some masses are set to 0, these can actually be computed analytically. So only the remainder would be done numerically. This again can be written as an integral of this discontinuity. It's now more complicated because of all those pieces that we subtracted, but it's the same idea as before. Now coming to the next master integral where I have an additional propagator. It's actually not much different than the one before. I only get an additional propagator term over here before I perform the last loop integration. But this is still this, okay, instead of an A0, I have a B0 function here. No big deal. Again, this is UV divergent. I somehow have to make it into something finite. Here I chose basically to use an integration by parts relation for that, where one gets a somewhat complicated expression of simpler integrals, and then this same integral, but with some of the propagators taken to the power 2. So I take basically the first and the fourth, the power 2, and then it turns out then it's finite. Finally, the most complicated master integral is the one with 6 different propagators. And so here I can again use the same philosophy of basically trying to imagine I cut up one line and then it becomes a two-loop integral, and I use a dispersion relation for the two-loop integral, and then I tie the last loop back together. Now, this two-loop integral that I get is not as nice as before, where it's just a product of two one-loop integrals. Here, it's a genuine two-loop integral. But the discontinuity of that is actually known, was computed by those people some number of years ago, and it can be written as a one-dimensional integral. So here I actually have an integral in here, and then I have the additional integral over S, so it becomes overall a two-dimensional integral for the finite result. And again, there's a finite piece which can be subtracted. Sorry, a divergent piece. So to finish up, basically, you know, all these master integrals can be expressed as numerical integrals of fairly low dimension. For two of them, it's just a one-dimensional integral. For the last one, it's a two-dimensional integral. There are a number of special cases for which these formulas that I showed you don't directly work, but they can be handled as well. This is in more detail in the paper. And all of this I have put into a computer code, which is publicly available. I call it TVID for free loop vacuum integrals with dispersion relations, which has two parts. One runs in Mathematica, and it basically subtracts, you know, all those expressions which are divergent and which can be done analytically. And then there's a numerical part which runs in C++ and does the numerical integrations. And on a single core, for the simpler master integrals, it takes a fraction of a second. For the more complicated master integral, it takes about up to half a minute to reach 10-digit accuracy. All right, so let me finish up. So I think numerical techniques, which were the topic of this session overall, are very promising for doing multi-scale, multi-loop integrals, which is something that, you know, in the current era of precision becomes more and more important to control. Nevertheless, there doesn't seem to be one method that works ideally for everything. So that's different. At one loop, you know, we have tools that work for all kinds of one loop problems very well. At two loop level and beyond, that's not quite the case. So for instance, there are situations for which sector decomposition is a great tool because it's so general and very automatized. There are other situations for which Mellin-Barnes integrals with this contour shift method work great. It's not as automatized, but can give you good precision. And if we go beyond the two-loop level, again, you might have problems for which you have dedicated techniques. For instance, if you want to primarily compute vacuum integrals, the method using dispersion relations for subloop bubbles works very efficiently. Thank you.
Could you go back to slide 8, please, where we had this problem integral?
Yes.
So, as you correctly identified, the problem is indeed that one of the internal masses is exactly the same as the x scale, and this means that the f polynomial goes like something like minus nzx something plus nz.
Yeah, sort of contour
so
yeah.
There's indeed no Euclidean region there, but in PySector, what we found was we could actually arbitrarily split the integration region in the bind parameter space at some random point and perform a sector decomposition. And then we kind of crossed the hyperplane singularity, and that got mapped to 1 or 0. And then sector decomposition can work on the split integral. And we actually...
So you have to split it even before you do the sector decomposition.
That's right.
I see.
Or you sector decompose, then you split, then you sector decompose again.
Mm-hmm.
And in that way, you can capture this particular case. And in the PySector paper, we actually sort of give basically the same result that you do here.
Oh.
So we specifically compute this because you pointed it out to us. What's clear is we don't compete with your timing. So I think you probably compute this much faster than we do. But just to say that...
yeah, again, but of course there's more human intervention that goes into it to
Sure.
these climbings. But yeah, okay,
Yeah,
very
okay,
good. So I need to update my slides. Yeah, thank you.
Yeah, just to say PySecDec can do
Yeah.
this is one of the improvements.
Please go back to the one more slide.
Mhm.
Seven. And part is
Yeah, so actually this this part would have no imaginary part. It would be zero. But you get something that's non-zero just because of limited numerical
I
precision.
see.
Yeah.
Thank you. Another question or comment?
And so, exactly in this calculation, I wonder why you didn't do an integral reduction. I mean, it's pretty impressive that you computed without an integral reduction, but was there a good motivation to not reduce them?
Well, so in total we have integrals where we have 3 independent scales. So if you do a symbolic integral reduction, I mean it becomes pretty marginal. I mean the expressions become enormous basically.
Yeah.
If we work together with some expert on some of these tools, I don't want to say it can't be done, but somehow you kind of have to make a decision at the beginning of the project. What you think is you can get done more reliably, and so we went this route.
Sure. Another question or comment?
Yes. The final state fermions, we basically take masses. So all fermions that are not the top quark, we just put the mass to 0. Yes.
I cannot clearly understand why M1 is top mass.
So this comes from the contribution if you had Z to BD bar. The final state bottom quarks are of course massless, but in the diagram you can have a top quark.
So 5 and 6 are W's there, right?
Yeah, so the idea would
to a top and then back to.
Right. So this is a bottom quark, here's a top quark, 5 and 6 are W bosons.
So this calculation, you only calculate the normalized delta part and the actual delta part, not the magnetic time.
Not the solid?
Magnetic time.
Magnetic time? No, only the vector and axial vector part. Yes. Yeah. Because that's the only part that's phenomenologically relevant for what has been done at lab and at the SLC. Right.
One more question. Father? Okay. So let's speak again and let's start all the discussion. Audience. Thank you very much. This session will be